Welcome everyone. This presentation is all about tables, Venn diagrams, and other diagrams and structures that you can use to help solve questions in Section 1, particularly the problem-solving subsection of Section 1 of the UMAT. So just to give you a better idea of where this video sits in relation to all the other ones, here's a layout of the channel structure. You can see here on the left we've got the UMAT exam broken into sections 1, 2 and 3. And under section 1, you can then further break it down into 3 subsections, which are problem solving, logical reasoning, and data interpretation. So these are the 3, broadly speaking, the 3 types of questions you can get in section 1. Now the problem solving are broken down into 4 videos, which give you 4 different types of techniques you can use. And this video obviously is T2, tutorial 2. So it's the first of the 4. And this is the order I recommend going through them in if you're going to go through all of them. So starting off with tutorial 1, which is the basic overview, and then moving into this one now, tutorial 2. And as you can see, we'll go through some more techniques later on for other problem solving questions. So let's get started. Tables and other structures. Rather than going through any theory, I think it's easier to just begin with some questions and I'll point things out as we go along. So here's the first question. As we go through, just pause the video if you want to have a closer read of the question before we get stuck into it. As you can see here, the question says that there are 4 doctors A, B, C and D, and they have 4 different specialties: surgeon, anaesthetist, radiologist and GP. And then we've got here 5 dot points which give us clues as to who might fit what role. So with these questions where you've just got the 2 categories, and by 2 categories I mean, first category is the people, doctors A, B, C and D, and the second category are their specialties, surgeon, anaesthetist, so on. The best way to structure this information and to bring all of the information you've got here into a nice, concise diagram or table is to sketch up a table like so, where you've got one category down the first column, which in this case are the people's names, and the second category, which in this case are the specialties, across the top row. So you actually have to write out doctors A, Dr. B, Dr. C, so forth, and likewise across the top with the specialties. In different questions that might not be dealing with people, and obviously might not be dealing with specialties, it could be dealing with, say, subjects at school on the one hand, and the classrooms in which they're taught on the other. So it can be quite different, but any question where you've just got the 2 categories like this one, that's the kind of table I would recommend sketching up. Once you've got that, you're pretty much halfway there. The next step is to go through the information and just tick or cross each box as appropriate or based on the information you've been given. So if we go to the top here, it says Dr. A is not the surgeon and has not seen the radiologist recently. So Dr. A is not the surgeon. That's a pretty concise and definite bit of information. So we can put a cross with the box that corresponds to Dr. A and the surgeon, because Dr. A is not the surgeon. Now, the second part of this dot point is a little bit more difficult. It requires you to take a step further. Basically, the first dot point implies that Dr. A is also not the radiologist, because Dr. A has not seen the radiologist recently. So, I mean, you can imagine it would be odd if Dr. A was the radiologist to give a sentence like that. It just wouldn't make any sense. So that means that Dr. A is also not the radiologist, and so we can put a cross in that box too. And it's just a case of going through in this way, dot point by dot point, and filling in the information as it comes along. So, second dot point, the anaesthetist and Dr. C have known each other the longest. So this information here about, how long they've known each other is irrelevant to the question, obviously. The thing you need to get from it is that the anaesthetist and Dr. C are 2 different people. Therefore, Dr. C is not the anaesthetist. So we can put a cross there with the Dr. C anaesthetist box. Third dot point, Dr. D and the GP travel to work together. So that's your first bit of information. Dr. D and the GP are 2 different people. So we can put a cross in that box too. And the second part of that dot point is that they often discuss their mutual friend, Dr. A. So what this implies is that Dr. D, the general practitioner, and Dr. A are 3 separate people. Because if any of them were the same, if there was any crossover, that sentence wouldn't make any sense. Just take a minute to think about that if it's not quite settling with you, that idea. But what that means is obviously Dr. D and Dr. A are different people, we know that. And Dr. D and the GP are different people, we know that, we've put the cross there. But the other step to make is that Dr. A also can't be the GP. So we can put a cross in that box there. The reason being, if Dr. A was the GP, that sentence wouldn't make any sense, because you could rewrite it as Dr. D and Dr. A traveled to work together and discussed their mutual friend, Dr. A, who's already been mentioned. So at this point, keep an eye on your table, because every now and then you get to a point where you have enough information to conclude something. So we can see here that Dr. A is not the surgeon, or the radiologist, or the GP. So Dr. A has to be the anaesthetist. So we can put a tick in that box there. Now if Dr. A is the anaesthetist, and there's only one anaesthetist out of the 4, that also means that you can cross out Dr. B as being the anaesthetist, and Dr. D. So basically when you tick something in one of these boxes, you can fill out the rest of that row and that column with crosses, which makes it a lot easier as you go along. It gets a lot faster once you get the first few bits of information. Let's go on to the 4th dot point. Dr. C and Dr. D travel to work in opposite directions. Now, when you look at that dot point by itself, it doesn't appear to give you any information, because we know that Dr. C and Dr. D are different people, and the fact that they travel to work in opposite directions doesn't seem particularly relevant. So if you ever see something like this, try and think a bit more deeply, and look to see if you can combine that dot point with another dot point to synthesize a new bit of information. So look at the dot point above again, and look at the 4th one, so the 3rd and 4th dot points, and try and see how you can look at them together to draw a new piece of information. We can see here that Dr. D and the GP travel to work together, whereas in the 4th dot point, Dr. D and Dr. C travel to work in opposite directions. So by bringing these two bits of information together, we know that Dr. C can't be the GP. Because if Dr. C was the GP, then these 2 points would be saying opposite things. One would be saying that they travel to work together, the other would say that they travel to work in opposite directions. So Dr. C can't be the GP. Once again, we've got a column here where we've got 3 crosses and only 1 empty box, so the tick has to go in there. We have to have Dr. B as the GP, and that means if Dr. B is the GP, they're also not the radiologist or the surgeon, so we can put 2 crosses in this row. Again, it's that case of crossing out the column and the row that any tick is put in. Getting towards the end now, last dot point, Dr. C always tells Dr. A about the last time she saw the radiologist. Again, it's similar to the first few dot points where it implies that Dr. C, Dr. A, and the radiologist are 3 separate people, because if they weren't, that sentence wouldn't make much sense. So we know that Dr. A can't be the radiologist, we've already got that crossed out. But we can also add the fact that Dr. C cannot be the radiologist. So I'll put a cross there. That just leaves the 1 box at the bottom for a tick, which means we can fill out the rest based on the fact that Dr. C can only be the surgeon, and we've already got the bottom row completed. So there you go, you've got all 4 filled out fairly quickly. And once you get used to this kind of technique, it can go much quicker than that too. And often there'll be 2 or 3 questions based off this one stem. So once you've got this, you can really get a few questions done quickly. So don't be afraid to take 4 or 5 minutes to construct this. So who is the radiologist? In this case, we can see that is Dr. D. So that's very much the approach I would take for any question where you've just got the 2 categories to deal with. When you've got 3 or more, the approach is a little bit different. I think this next question demonstrates that pretty well. For those of you who have seen the video before this, which is called Section 1, the Basics, you may have seen this question before. The reason I've included it again is because that was made a few years ago, and at that time, the technique I used to solve it in that video does work, but I found a better one since then, and one which is much quicker. So if you like the technique used in the previous video, then that's totally fine, but I'm going to show you another one which is even better, I think. So here's the question. As you can see, we've now got 3 categories instead of 2, because we've got 1 the men, 2 the women, and 3 the months of the year. So as you can imagine, we can't necessarily draw one table in a similar style to how we did in the first question and fit everything into that, because we've got 3 variables rather than 2. So what do? Well, you could either do what we did in the previous video, if you've seen that, and draw up a few different tables and do the tick and the cross method, or you can do what I'm going to show you now, which is to draw up a table like this. So you can see it's fairly similar to the first question. We've got one of the categories written out in full down the first column. So we've got all 5, in this case, months written out here. But across the top, you can just see that we've got men and women. So whereas in the first question, we actually wrote out all the different specialties, so we wrote out GP, surgeon, etc. In this question, we're just writing the name of the category, men and women. So that's the slight difference in the way you construct the table. You write one of the categories out in full, down the first column, but the remaining categories, you just write the name of them across the top. Now the reason for that is that we're not going to do the tick cross method here. We're going to just put the various men and women straight into the table. So at this point, again, you're about halfway there at this point if you can construct that table. From here, it's just a case of going through the dot points and working out what we can get from that. So the key thing here is to put in the information which is definite. So you want to start with the information that you know you can put in for sure. So if we look at the first dot point, Charlie's wedding was in March. That's nice and definite. So we can just go to March and we can put Charlie in here under the men. The next dot point, Bob was married in May but not to Jessica. Well, we can see that the first half of this is definite because we can put Bob in here with May. But the second half, not to Jessica, that's not really definite. We know that he's not married to Jessica, but there's still 4 different people that he could be married to. So for now, we'll just leave that. Third dot point, David married Izzy in the month after Hillary was married. Again, there's no part of that information which we can put straight into the table at this stage. So we'll skip over to the final dot point, which is Fiona was married in January but not to Edward. So we can put Fiona in January, but again, we can't put anything about Edward or a potential spouse in there. So at this point, we've put in the definite information, and that's the first step once you've constructed your table, is put in the things you know for sure. Once you've done that, it becomes much easier because you've already filled up a few spots. So the number of remaining spots obviously gets less and less. And that means that the dot points that you couldn't put in before, you can start to be able to bring them in as you progress. So if we look at the first dot point again, we can see that we've got everything we can from that. So we can't get any more. Second dot point, Bob was married in May but not to Jessica. Again, we've got Bob in there already. There's still 4 variables or 4 different women that he could be married to. So again, we can't put anything more in at this stage. If you look at the third dot point though, David married Izzy in the month after Hillary was married. So just take a moment to think about what needs to be, or what you need to have in this table. You need to have David and Izzy on the same row because they're married to each other, so therefore they're married in the same month. So already we're down to February or April because they're the only 2 rows where there's 2 gaps. And the other condition is that they were married the month after Hillary was married. So we haven't got Hillary in there just yet. But if David and Izzy got married in February, that would mean that Hillary would have to be married in January. But we can see here that January is already occupied by Fiona, so they can't go in February. And that just leaves us with the one row, which is April. So the only row that David and Izzy can both be in and still be married in the month after Hillary is April. So we'll pop them in there. And given they're married in the month after Hillary, we can put Hillary up there in March as well at the same time. So already you can see how much easier it is when you get just a few names in the table. Dot points that you couldn't really use before all of a sudden become usable. So we'll keep going. We can see that Fiona was married in January, but not to Edward. So Fiona wasn't married to Edward, and there's only 2 spots left for the men. So if Edward wasn't in January, that means he has to be in February. So I'll put him there. And the only man remaining at this point is Alan. So Alan has to go in January. Also keep a look at what the question's asking you, because at this point we can actually answer the question without worrying about the last 2 spots. So in the real exam, you just go for option B at this point and keep going. But let's just finish it off. So the last two, let's have a look. Fiona was married in January but not to Edward. We've got that. Bob was married in May but not to Jessica. So Bob is not married to Jessica. So Jessica can't go in May. That means she has to go in February. So I'll put Jessica there. That means the last remaining person is Georgia. So I'll put Georgia there. And so yeah, again, if you saw the previous video, the one where I showed the different technique of how to come to this conclusion and how to, come to the ultimate finalized table, you'll see that it's a lot longer and there's a lot more room for error. So I think this is a much quicker way of coming to an answer in any question where you've got 3 or more categories. So I'll put the answer in there as B, January, and move on to the next question, which again is very similar. This one we're going a step further. So now we've got 4 different categories. We've got the people. As well as that, we've also got the sports, the days of the week they play, and the colors they wear. So 4 different categories. The way we solve this is very similar to the question before. We'll make a table. So again, pick one of the categories. I often just use the people's names to write out in full down the first column. And then across the top row, just write the names of the remaining categories. Don't write them out in full, just the title or the name of those categories. So just sport rather than all the sports. So sport, day, color. At this point, it's the same process. Go through the information, in this case the dot points, and begin by pulling out the really definite bits of information. So if we go through, you can see that the first 2 dot points, you can't put anything definite in from them. They've got some information, but nothing you can put straight into the table at this point. Whereas the third dot point, Chris plays tennis, you can put that straight in. So Chris, sport, tennis. There's 2 other bits of information we can get from here which we can put straight in. One is that Danielle plays in blue, so we can put Danielle, color, blue. And it doesn't matter if the second half, if we can't do anything with the second half just yet, that's right, we can just take the first half, which we have. And the last bit is Brendan plays on Friday. So Brendan, we can put Friday under the day. So just like the previous question, we've got, 3 or 4 bits of information we can put in straight away. And once you've done that, it becomes much easier to put in the rest. So let's go back through the dot points and see what we can do now. First dot point, the person who plays soccer plays on Saturday. So really we're looking for a row where both the sport and the day column are empty, because we need to get both soccer and Saturday on the same row. At this point, both Amy and Danielle have rows where both sport and day are empty, so we still can't put it in. But you can see already we're down to 2 different people rather than 4 at the start of the question. So already it's much easier and we're getting much closer. Second dot point, again, it's the same problem. So we need to have Monday and red on the same row. And so we need to look for a row where both the day and the color are empty. So that's Amy, and that's also Chris. So unfortunately there's 2 of them, we can't be sure, so for now just leave it. If we come down to the 5th dot point, however, the person who plays basketball wears yellow and doesn't play on Friday. So we need to ask ourselves who this person is. So for one thing, they play basketball, so anyone who already has a sport filled out can't be that person, so it can't be Chris because Chris plays tennis. This person doesn't play on Friday, so it can't be Brendan because Brendan plays on Friday. And this person wears yellow, so it can't be Danielle because Danielle wears blue. And so just like that, we've crossed out Chris, Brendan, and Danielle in that order, which leaves us with Amy. Or the alternative way to do that is just to go row by row and look for a row where both the sport and the color columns are empty, and also there's no mention of Friday in the day. But you come to the same conclusion that only Amy can be this person. And so we can put in basketball and yellow into her row. At this point, just keep going through the dot points. So go back to the top. The person who plays soccer plays their game on Saturday. So remember last time we looked at this dot point, it could have been either Amy or Danielle from memory. But at this point, we've got more information. So the person who plays soccer plays their game on Saturday. We need to find a row where both the sport and the day are empty. And at this point, because Amy's been added to basketball, only Daniela's left. She's the only one out of these 4 people where both sport and day are empty. So we can put those 2 in. At this point, you can see the sport column is all filled apart from just one. So we can look for what the remaining sport is, which is cricket, and we can pop that in. Keep going back to the dot points and just go round and round. So first dot point's now done. Second dot point, the person who plays the game on Monday wears red. So we need to find a row where both the day and the colour cell are empty, and that has to be Chris. It's the only option we've got left, so we'll put that in. And now it's just a case of filling in the remaining day, which is Wednesday, and the remaining colour, which is green, because they were just the only ones left. And you can see just like that, you can fill out the whole table. And it's just a case of knowing how to sketch up the table, and then being good and very logical when it comes to going through the information and starting with the definite stuff and working through it systematically. But again, you can take, generally, check how many questions you've got attached to the stem, but often it'll be 3 or 4. So you can take a good number of minutes to construct this. As you can see, once that's done, the questions will be pretty simple. So in this case, which of the following can be concluded? We can see there that the answer is A. I would say about 90 to 95% of questions where you're or where you're given a few different categories and asked to work out what matches with what, such as we've seen in the first 3 questions, will be very similar to the first 3 questions, and you'll be able to use the techniques we've used so far to solve them. And really it's just a question of whether there are 2 categories or components, in which case you should use the technique we did in question 1, or are there 3 or more categories or components, in which case we should use the technique we did in this question and the last one. But that's really all there is to it most of the time. There's one exception I think I should go through, which is shown by question 4. If you look at this question, and I should say now you wouldn't get this table given to you, that's obviously just what you would have to sketch up on the side of the page. But looking at the question now, it looks like it's pretty similar to the previous 2 questions. We've got 3 components or 3 categories. We've got the friends or the girls, their clothing items, and the colours. So 3 different categories, just like the previous couple of questions. The real or the main difference in this question to the previous ones is that there's repetition of both colours and of clothing items. So in other words, every girl will be wearing shoes, a skirt and a top, and those garments will be white, blue and red, just in a different combination. So there's repetition of the various components, which is the difference between this question and the previous one. If you see this, odds are the question will be in this style, where you're basically asked to work out who's wearing what colour what, or a variation of that depending on the story you're given. And the way I approach this, it's kind of a hybrid of the technique we saw in the first question and the technique we saw in questions 2 and 3. You can see down here I've picked one component, which is I've just gone with the girls' names and written them out in full down the first column. And I've picked a second component, and I've gone with the different clothing items, and I've written that out in full across the top. So at this point it's almost like the first question where we wrote out, if you remember, the different doctors down the one side and the different specialties across the top. So you're writing out everything in full. At this stage though, the technique turns more into what we saw in questions 2 and 3, where rather than doing the tick and the cross technique, we're actually putting the colours, in this case, straight into the table. We're putting them directly into the table. So the way to do that is just to look at the information given to you. Now in previous questions we've had usually 4 or 5 dot points of information. In this one we've just got one sentence here, which says, what colour are Sophie's shoes if she wears a white skirt and Emma wears white shoes and a red skirt? So let's put that information in, what we know for definite, for sure. If Sophie wears a white skirt, well, let's put a W in there under Sophie and skirt. And if Emma wears white shoes, so we'll put Emma shoes white, and a red skirt, we'll put R there. That's all we've got. That's all we've got that we know for certain. At this point, it's a case of working out how you fill in the rest. And the key here is to realize that each of the 3 girls is going to wear these 3 items, and they're all going to have one item of each colour, which means that in every row you have to have one of each colour. And it also says that none of them want to wear, it also says that none of them want to wear a particular clothing item of the same colour as someone else. So if that means that, for example, Emma's wearing white shoes, no one else will wear white shoes. So not only do we have every row containing one of each letter or one of each colour and nothing more, we also have every column, so every column doing the same, just one of each colour. So it kind of turns into a bit of a Sudoku, where you just need one of each in each column and each row. And so it becomes quite simple. You can see the top row here. We've got one white, one red. So we have to go with blue here to finish out the row for Emma. Likewise with the middle column, we've got one red, one white. So I have to put one blue there. At this point, there's a few different ways you could do it. I'm going to say that because we've got a white pair of shoes and a white skirt, really the white has to go here, because can't go here, can't go there. It's got to be there. It just wouldn't work anywhere else. You'd have repetition. At this point, you can complete the bottom row. You can say that that should be red because it's the only letter remaining. Then this first column, got to put blue in there, and just to finish off, red in here. And so just like that, even though you've just got one sentence of information given to you, you can work out all 9 pieces of clothing. And again, the question now is pretty simple. What colour are Sophie's shoes? It's just a case of reading off, and you can see blue. So these first 4 questions are all quite similar, as I've mentioned before. They're all asking us to look at a few different categories and a few different elements within those categories. And the fundamental part of the question is that you're being asked to work out what corresponds to what. And so the tables we've seen in the first 4 questions, I think, are the best approaches to the variations you can see amongst this style. Moving on now, we're going to go to a different type of question, a different style, and that is any question where you're asked to rank things or just put them in a certain order. So question 5 here demonstrates that pretty well. Just pause the video again and have a read of that if you want to try and solve it before we go through it. So in this question, we're really being asked to rank these people from top to bottom in terms of their position within this apartment block. So as might be quite instinctive to you, the best way to begin solving this question is to sketch up something representing the apartment block, which kind of takes the form of a table, albeit a pretty simple one. I would do something similar to this, where we've simply got the 10 levels from top to bottom, and be sure to be very careful with reading all the question and every detail of the question, because as you can see here, the top level is level 10, going down to the bottom, which is level 1. So obviously if you had that the wrong way around, that would throw the whole question out right from the start. Once we've got this, it's just a case of going through the information given to you as we did before, and putting it into the table as we are able to. So let's begin with what we know for certain, and we get quite a lot of information from the question stem itself up here. So we can see Tim lives on level 10, so we can put Tim straight in the table because that's a definite bit of information. David lives on level 8, so I'll put Dave in 8, and just keep going through here with Monica, Oliver, and Jack. So pop them into the levels that they belong to. At this point, that's all the information we get from the stem, but we've got some dot points here too. The key thing again, as we did before, is to pick out the dot points which provide you with definite information at this point. So for example, that top dot point, Sarah lives on a lower level than Tim. Well, we can see that Tim lives at the top level. So that means Sarah could live anywhere else, any of the levels below him. So that really hasn't given us any new information at this stage. So we'll leave that for now. If we go through the dot points, the one which provides the most definite information at the moment is the third one. Derek lives on the lowest level. Very clear, very straightforward. We can put Derek right in the bottom on level 1. Now we can keep going through the dot points and start looking at what is the next most definite. So again, that top dot point doesn't give us a great deal. That means Sarah could be anywhere for now. If we go to the second dot point, Oliver lives on a lower level than Georgie. Well, we've got Oliver in the table already, and he's sort of in the middle there, which is helpful, because it means that Georgie has to be above him, according to the second dot point. So Georgie has to be either in 7 or 9. What I like to do at this point is just put in a couple of G's there to say that Georgie has to belong either there or there. Going through the dot points again, we've got everything we can out of the third dot point. If we go to the bottom one, Rachel lives in a higher level than Eric. If you look at the table, we can see that neither Rachel nor Eric is currently in the table, which is a bit difficult. But what I like to do in this situation is to draw up something like this, just to show that when they are put in the table, or if they are able to be put in the table, Rachel needs to be positioned higher than Eric. So this represents their positions relative to each other in the table. And just finishing off, you can see that Sarah lives in a lower level than Tim. Even at this point, right at the end, that doesn't give us any more information. So Sarah could be anywhere out of these 4 spots. The other thing I like to do at this point is just make sure that everything is accounted for. So make sure you've got the same number of names as you do spots left in the table. So we've got 4 spots here in the table, 9, 7, 4 and 2, which are unfilled at this point. And we've got Georgie, Rachel, Eric, and I'll put there Sarah, just showing that Sarah could be anywhere from 9 through to 2, because the only condition on her is that she has to be below Tim, who's up there in 10. So at this point you can see we actually can't fill out the table. It's not possible to do it based just on the information we've been given here. Unlike previous questions we've done in this video where you've been able to fill it out completely, there are some questions where it's just not possible. So at this point, appreciate that that is the case, that you can't get any further than this, and have a look at the question itself, because often you don't need every bit of information completed to solve the question. That's just the way that the question itself is designed. So, which of the following must be true? A, Eric lives below Georgie. I should say at this point that if you're ever faced with a question, which of the following must be true, it's not enough to just show that it can be true. You have to show that it is always true. So it can be a bit confusing, but often the best way to do this is to try and disprove it. And if you can't do that, it's the correct answer. So in other words, which of the following must be true? Eric lives below Georgie is option A. If you can show that there's a situation where Eric lives above Georgie, not below, then you've crossed that option out. Because by showing that the opposite can be true, it means that that option isn't necessarily true, or it's not definitely true, as the question asks. So if we go through that technique, which again, it's a bit confusing at first, but it is the most definitive way of getting to an answer, let's evaluate option A now. Which of the following must be true? Eric lives below Georgie. Let's try and show that Eric could live above Georgie instead. So Georgie could go either in 9 or 7. If we want to show that Eric could live above Georgie, we'll have to put Georgie in 7 so that there is an empty space above her where we could put Eric in potentially. So if we imagine putting Georgie in 7, we then have to have Eric above her in 9 to satisfy what we're doing with option A. But at this point, you can see that Eric needs to be positioned below Rachel as per the 4th dot point. And so if we put Georgie in 7 and Eric in 9, there's no spot above Eric where we could put Rachel. So that can't be true. So in other words, the inverse of option A, the opposite, which we were trying to prove, which is that Eric could live above Georgie, we showed that that isn't the case, that we couldn't have a situation where Eric lives above Georgie. And therefore, which of the following must be true? Well, it must be true, therefore, that Eric lives below Georgie, because we've disproved the fact that he can't be above. So option A is actually correct in this situation. I'm just going to go through option B now using the same technique as I just did then, just in the hope that it might clarify it even further. So at this point we know that option A is correct, but I'm just going to go through option B and evaluate it just to demonstrate. So option B is that Sarah lives above Dave. So certainly it can be true that Sarah could live above Dave. We could put Sarah here in 9, which would be above Dave, who's in 8. And then to satisfy the rest of the conditions, you could put Georgie in 7. Because remember, Georgie has to be either 7 or 9, and we've already got Sarah in 9 at this point. So Sarah in 9, Georgie in 7. And the only other condition is that Rachel has to be above Eric, as we've got here on the right-hand side. So we could just put Rachel in 4, Eric in 2, and that would satisfy all the conditions. We'd have these 4 people in positions which are appropriate and which fit our 4 dot points here. So it's true that Sarah could live above Dave, but the question's saying which of the following must be true. So is it possible that actually Sarah could live below Dave? Well, to try that out, I'm going to put Sarah down here in number 2. So we're putting Sarah in 2. At this point, I'm going to put Eric in 4 and Rachel in 7. Because remember, the only condition with those two is that Eric has to be below Rachel. So at this point, I've got Sarah in 2, which is below Dave. Eric in 4, Rachel in 7, which satisfies that condition there about Rachel being above Eric. And we can still put Georgie up here in 9, which is fine because the only condition about her was that she has to be either in 9 or 7. And you can see that by doing so, we've again satisfied all the conditions. That table where we've got Georgie in 9, Rachel in 7, Eric in 4, and Sarah in 2 satisfies all of the conditions of the question. And it also means that Sarah can be below Dave because in this situation she's in level 2, which is definitely below Dave in level 8. So, which of the following must be true? Sarah lives above Dave. That's incorrect because as we've shown, she can actually be below Dave. And so that's what I mean by trying to prove the opposite of each of these multiple choice options. And if you can prove the opposite, as we've just done with option B here, that means you can rule out that option. That option is incorrect. And if we went through options C and D, which please feel free to do now, you would find the same thing, that Jack could live either below Eric or above Eric, and that, well, in this case with Derek, he's right at the bottom, so we know that he definitely can't live above Georgie. And that's why, as we showed before, option A is correct. I'm just going to go through one more technique you could use in a situation like this, and indeed any situation in UMAT where you've got a table or some set of data which is almost complete, but we've got a few variables as we have here, a few different variations of the table we could have. In situations like that, if you've only got a few different possibilities, you can actually write out all the different possibilities into another table. This is something just extra, you don't have to do it if you're not comfortable with it, but I'm going to show you quickly how to do it now. So I would sketch up something like this. What we have here on the left hand side are the 4 different levels, 9, 7, 4, 2, which are the 4 empty levels we have here. And then filling in, and across the top, are the different possibilities for the 4 different people we have remaining and which levels they could occupy. So it looks a bit confusing at this point, but it's actually quite simple. So we've got 1 here, which means the first possibility is that Greg could be level 9. Georgie could be level 9. Rachel level 7, Eric 4, and Sarah in level 2. That's one set of possibilities that would satisfy all of the information. You can see here, number 2, this is just the second set of possible of the possible order of the people, and we go across 3, 4, 5, 6. So we've got 6 different possibilities for how the people could be arranged across those 4 levels, while still satisfying all the conditions of the question. In terms of how to construct this, it's actually relatively simple. I start, for example, in this question with Georgie, because Georgie is the one who we've got only 2 different possibilities, 9 or 7. So I begin by putting her in 9. Then look at the next condition, which is that Rachel has to be above Eric. So we could put Rachel, as I've done here, in 7, Eric in 4, and then Sarah could go anywhere, remember? Because the only condition on her is that she has to be below Tim. So I'll put Sarah down there in the last remaining spot at the bottom. That's why this set of people, in this order, could satisfy every condition. Keep moving along, keep Georgie in 9, as we did before. Keep Rachel above Eric, as we did before again. And then in this case, the only difference is that I put Eric in the bottom in 2 rather than in 4. And that just means that Sarah now shifts up from 2 to 4 to replace him. But still, all the conditions are satisfied. Georgie's in 9, Rachel's above Eric, and Sarah's filling in the gap. Same here, Georgie's still in 9, Rachel above Eric, but again their positions are different from the previous 2 sets. and Sarah in that remaining spot. And then the last three are much the same. I've just started with Georgie in 7, which is the other position she could be in, and put the other people around her in an appropriate way. So that's a different way of doing it. You need to be down to only a few different possibilities, such as 6 in this case. But the advantage of that is once you've constructed it, it's very quick to go through it and see what the answer is. So if we were evaluating this question here, for which we know option A is the correct answer at this point, if we were trying to prove A, Eric lives below Georgie, we can just go through each of these 6 different sets of possibilities and look at where Eric is relative to Georgie. And you can see in every situation, Eric is living below Georgie. Georgie, Eric, Georgie, Eric, Georgie, Eric, so on. Across all 6 of them, Georgie is always above Eric. Or to rephrase, Eric is always living below Georgie, which is why option A is correct. Whereas if you look at option B, Sarah lives above Dave. Dave's in option 8, which is kind of in between 9 and 7. So we're looking, as we look across the 6 different sets, we can see there is one situation here where Sarah is actually above Dave, and the other 5, she is below Dave. So actually she doesn't always have to live above him. In 5 of the situations, she can be below. That's why B is incorrect. And if you look at C and D and go through the same process of looking at the 6 different data sets, 1, 2, 3, 4, 5, 6, you'll see that there isn't, or in some cases, Jack will live above Eric, and in some he'll live below. Whereas with A, it's definite across all 6, which is why it's the correct answer. We'll move on to question 6 now. Take a minute again to have a look at this question. You can see that even though the story is very different from the previous question, insofar as this one is about a race, whereas the previous one was about the levels of the apartment block, the basis of the question is quite similar, because we're again being asked to rank people in a certain order. The other key difference with this question, I think, is whereas in the previous question we had reference points, in other words, we were given that, for example, so-and-so lived on level 8, in this question we've got no such reference points. All the information we're given here is about one person relative to another. So in other words, Andrew's heat was after Jill's. We don't know, for example, here if Andrew was towards the top or towards the bottom. We just know that he was before Jill. Similarly, we don't know if he was right before Jill or if there were several people between them. We just know about that relative information. So the way we go about this question is a little bit different. We can't sketch up a nice table with a definite number of levels as we did in the previous question, where we had the apartment block sketched up with all 10 levels, because we just don't know where people are placed when we start putting information in this question. So that's the main difference between this question and the previous one, and I think that's the distinction to pick up on any question where you're asked to rank people in a certain order. Ask yourself, have I been given definite reference points? If you have, approach it the way we did in the previous question. If not, use the approach I'm about to show you here. So that's the main thing. The other key thing with this particular question is to pick up on the fact that there are 2 distinct things we're looking at here. One is the heat order. So in other words, the order that the people went in, because obviously this race was done 1 by 1, so people had separate heat times, separate orders. That's the one hand, the heat order. On the other hand, we've got their times. So in other words, fastest to slowest. So there's 2 distinct things we're dealing with here. And if you go through the 4 dot points, you can see that, roughly speaking, the first half of each dot point deals with the heat order, so the order that the people went in. For example here, Andrew's heat was after Jill's. And the second half of each dot point, generally speaking, is about their times. So Andrew's time was slower than Kevin's. That's dealing with the speed they went at. So there's 2 distinct things we're dealing with here. And because of that, I'm going to keep it separate and go and write down here heat order, so the order they went in, and heat time, which was their time or their speed. At this point, like I mentioned before, we don't have any reference points, so all we can do is put names in and position them relative to other names and slowly build up a picture of where everyone was relative to everybody else. I'm going to begin with the order they went in, so that the heat order here, and go through the dot points. Now, I think that the key thing at this point too is that you want to pick a name which you can see quite a lot. because you want a name which is mentioned a few times relative to a few different people, as that'll make starting this process much easier. There's a few different options you could go for in this question, but I'm going to go for Rory, because I can see him a few times here and there. So I'll put Rory down just somewhere in the middle in our heat order. So eventually this heat order column is going to be everyone's name, or everyone's names, hopefully, from the top, which would be the first person who went, through to the bottom, which would be the last person who went. At this point with Rory, we don't know if Rory will end up towards the top or the bottom or in the middle. So when you're doing this in the real paper, leave a lot of space around the names and just put them somewhere in the middle to start with, because you don't know which way it's gonna build. Let's now look at the dot points which relate to Rory in terms of the order that he went in relative to other people. So we can see here there's one bit about Maddie's heat was after Rory's and before Kevin's. So the wording's quite tricky. Just think about what that means for a minute. Maddie was after Rory and before Kevin. So the order from top to bottom will be Rory, and then Maddie, and then Kevin. And so we can put that down here on our heat order. Rory, then Maddie, then Kevin. Which is a good start, because we've got 3 people down already, and now we can use that to build off. So looking at the next dot point down, Rory's heat was after Andrew. So that means we can put Andrew above Rory in terms of the heat order, which I'll do now. And you can see from here we've got 4 names, and you can really use any of them at this point to keep building. So going back to the top, Andrew's heat was after Jill's, so we can put Jill above Andrew. After that, the dot point turns into heat time rather than heat order, so we'll leave that for now. Second dot point, Cassie's heat was before Nick's and after Kevin's. Again, worded a bit trickily, quite difficult, so just think about what that means. Cassie was before Nick and after Kevin. So Cassie was after Kevin, we can put Cassie down here below Kevin, and Nick was even below Cassie, because Cassie was before Nick. So in other words, after Kevin, we need to have Cassie, and then below Cassie, we need to have Nick. And at that point, I think that's all the information we can get based on the heat order. And if we go through the 4 dot points and just look at the parts of them which relate to the heat order, you should be able to see how that list from top to bottom fits in with all the information. The other thing to do at this point, as with the previous question, is just count up all the different names you know you need to account for, and just see if you have accounted for them, or if not, how many are missing. So in other words, in the question here, we've got 1, 2, 3, 4, 5, 6, 7, 8 people. And in the heat order we've got 1, 2, 3, 4, 5, 6, 7. So it's very easy to miss that, but we are still missing 1 person. And if you go through the names, I believe that would be Trevor. So we don't have Trevor at this point in the heat order. That's okay. The questions are sometimes designed this way, that you can't complete them, as with the previous question. All it means is that Trevor obviously did have a heat. We just don't know if he was first or second or third or last. Could be anywhere in this list. You could put Trevor in. We just don't know. As you can see above here in the dot points, the only mention of Trevor is with respect to heat time, not heat order. So there's nothing we can do at this point. And that's the best we can do for heat order. If we move on to heat time, which in other words is the speeds that each rider went at, we're going to rank these again as we did with heat order, but this time we're dealing with the time. So fastest at the top, down to slowest at the bottom. It's the same process. We begin with any name, but ideally one where you can see quite a few references to. I'm going to begin with Andrew, so we can see Andrew here and again at the top. So start at the top dot point and see what you can get about Andrew's heat time. Andrew says Andrew's time was slower than Kevin's. So we'll put Kevin somewhere above Andrew. And again, just to mention, in the real paper, you don't know if Kevin's going to be right above Andrew, as in immediately before, or if he's going to be well ahead of. So you've got to leave a bit of space between all the different names you put down. So we've got Kevin above Andrew. If we go to the bottom dot point now, just because we can see again Andrew and Kevin mentioned again, which are our reference points at this stage, we can see that Rory's heat was, or Rory was faster than Kevin. So we've got to put Rory above Kevin, like so. There's another mention of Rory here in the above dot point. So we'll look at that one. It says that Maddie was slower than Trevor and faster than Rory. So what that means is we need to have Maddie immediately above Rory and then Trevor above her. So that way with Trevor, then Maddie, then Rory, that makes sense with this third dot point. Maddie was slower than Trevor and faster than Rory. And just to go to the final dot point we haven't looked at yet, which is the second one, Cassie's heat is before Nick's, and she was faster than Trevor. So Cassie was faster than Trevor, which means we can put Cassie right at the top here. Again, there are two names you haven't accounted for at this stage, which I believe would be Jill and Nick, but there is no mention of Jill or Nick with respect to the heat time anywhere in the question. So we just don't know where they fit in. They could be fastest, they could be slowest, could be in the middle, we don't know. But just keep in mind that we haven't put them in our little lists just yet. So let's go to the question. Which of the following must be true? A. Andrew's heat was second and he was the slowest. So that may look pretty good. So Andrew's heat was second, that's dealing with the order of the heats. And he does appear to be second here. Likewise, saying he is the slowest would appear to be accurate because he's right at the bottom here of the heat time. The little trick here with this option is that, as I mentioned before, we haven't accounted for all the names. So Trevor, we know, had a heat. We just don't know when it was, if it was first or second or last or anywhere in between. So if Trevor did go first in the heat order, if he was in here just above Jill, then all of a sudden Andrew would be the third. His heat would have been third, not second, which is why we can't say that A is definitely true, because if Trevor was above Andrew, then Andrew would shift down to third, not second. Likewise with the slowest, the two names Jill and Nick we didn't account for with heat time could be below Andrew here. So if that was the case, he wouldn't be the slowest. That's just the trick with option A. It's checking to see if you've accounted for all the names. Option B, Kevin's heat was before Cassie's and he was slower than Rory. So Kevin was before Cassie in terms of heat order. That seems to be accurate. Kevin is above Cassie here, and he was slower than Rory. Again, seems pretty good. Kevin is below Rory in heat time, so he was slower than Rory. Now you can see that with option B, it's not giving you any reference points as it did with option A. In option A, we had Andrew was second, and we couldn't conclude that because there were still people unaccounted for who could change Andrew from currently being second to being third. With option B, it's just saying that Kevin was relative to Cassie. It's just saying that it's giving information about Kevin's position relative to Cassie and to Rory. Now, it doesn't matter where you put the missing names in to the heat order or the heat time. It doesn't matter where you put Trevor in here or where you put Jill and Nick in here. Kevin will still be before Cassie, and he'll still be slower than Rory. Doesn't matter where they go. The relative positions of the names you've got in the table will stay the same. And given that information is consistent with what we have here, option B is correct. The other two options, Cassie's heat was first and she was second slowest. That's the same trap as option A, where it's giving you specific places, which we can't conclude because there are still names unaccounted for. And with option D, Maddie's heat was after Nick. We can see that that's just wrong because Maddie was before Nick. So it's just getting the order mixed up. And because of that, we can say that option B is the correct answer. Let's move now to the next question. Again, take a minute just to have a read of this one. As you can see, the situation here is we've got 6 seats in a row, and there are 2 conditions that we have to abide by. First of all, there may be no more than 2 children at the table, with the remaining seats filled by adults. So take a second to think about what that means. It means that we either have to have 0, 1, or 2 children out of the 6 seats, and the remaining spots are filled by adults. So either 0, 1, or 2 children, but no more. The other condition is that any child must not be sitting next to exactly one adult. So that means that any child at the table has to be sitting next to either no adults or 2 adults, but not 1. Again, it just helps to take a second to think that through and to process it because it makes the working out much quicker once you've got that. So how do we work this out? It's actually quite similar to what I did a couple of questions ago with that apartment block question, where at the end I sketched up that table with the 6 different possible configurations. That's what we're going to do now again pretty much. It's just working out all the different configurations. that we could have in those 6 seats that satisfy both condition 1 and condition 2. So I'm going to sketch up a table like so. What we have here is the 6 different seats from left to right, and down the first column here we've got all the different combinations we could have. So in other words, number 1 here will be the first set of adults and children that satisfy both condition 1 and condition 2. Now obviously when you first start doing the working for this question, you won't know how many different rows to have, which represent how many different configurations there'll be, because at this point we don't know if there'll be anywhere from 4 through to 12 configurations. Could be any of these, so we don't know how many rows to do. So just leave a bit of space when you're working it out. In terms of beginning the process of filling out the table, I always look for a natural structure. So in this one, the thing that jumps out at me is that there may be either 0, 1, or 2 children as per this first condition. So I'm going to use that as a natural structure for filling out this table. I'm going to begin just by looking at if there are 0 children and work out all the configurations for that, and then go look at if there was 1 child and all the different configurations for that, and finish off with 2 and then add them all together. So if there are no children, that means that we're going to have all adults. So I'm going to write an A in each of the 6 seats just to show that there are adults in all 6 seats. Now, does this satisfy both conditions? Well, yes, it does, because it satisfies the first one because there are no more than 2 children, because there are none, and it satisfies the second because there are no children, and therefore this second point about any child sitting next to only 1 adult isn't really relevant. So configuration number 1 is fine. This is one configuration that could be achievable according to the conditions we've been given. As you can see there, there's not really any way we can change that up. So in other words, this is the only configuration you can have when there are no children, because you've only got adults there. So however you mix them up, it's going to be the same configuration. Let's move on now to if there's 1 child at the table and the rest filled by adults. So imagine you put the child here in seat 1 and the remaining seats are filled by adults. Ask yourself if that would fit the 2 conditions. Well, it would fit number 1 because there are no more than 2 children, but it wouldn't fit the second because that 1 child sitting in seat 1 would be sitting next to 1 adult. And the second point says that any child must not be sitting next to exactly 1 adult. So we can't have a child in seat 1. What about seat 2? I'm going to put a child in seat 2 and adults in the remaining seats. So does this configuration work? Well, again, it satisfies the first point because we've got only the 1 child now, which is no more than 2. And the second point is also satisfied because this child here is sitting next to 2 adults, 1 on each side. And because that is not exactly 1, it satisfies that second condition we have here. So this is another configuration, another possibility. And we just keep going like this. So the child could be in seat 2. If we put that same child in seat 3 and put adults in the other spaces, again, it works fine. We've just got the 1 child there, and that child is sitting next to 2 adults. So both of these 2 conditions are satisfied. Shifting along, if the child goes there, adults in the rest, it's the same thing. That again works. And one more time, child there, adults there, it's fine again. You couldn't put the child in the final seat, in seat 6, because you've had the same problem as when we had it in seat 1, insofar as it would be sitting next to only 1 adult, which goes against the second condition. So these 4 rows here, rows 2, 3, 4, and 5, represent the 4 different configurations we can have, where there's just the 1 child. And we can be pretty sure that that's all there is because we've gone through systematically from seat 1 through to seat 6, putting the child in each of those and seeing if it satisfies both conditions. So at this point we've looked at if there are no children, which is row 1. We've looked at if there's 1 child, which are rows 2, 3, 4, and 5. The last thing to do is work out how many different configurations there are when there are 2 children at the table. So let's work out where we can put these 2 children. Again, we can't put the child or either of the children in seat 1, because if you imagine putting a child there, we'd either have to put a child next to it again, in which case that child in seat 2 would be sitting next to 1 adult, which goes against the second condition. Or if we put a child in seat 1 and then an adult in seat 2, that first child in seat 1 would be sitting next to 1 adult, which again goes against the second condition. So however we do it, we can't have a child in seed 1. It just doesn't work. If we look at seed 2, we can put a child in seed 2, so I'll put one down there. If we did that though, we'd have to have an adult on either side of it. So we'd have to have adult there and adult there, which means the next seat a child could go is seat 4. I guess another way of thinking of that is if you put a child in seat 3 and seat 2, then both of those two children would have just the one adult sitting next to it. So that's why this is the next best we can do. And if we fill out the remaining seats in that row with adults, you can see that that would be fine. That would satisfy both condition 1 and condition 2, because both children are sitting next to two adults. Let's work out more configurations from here. So if we put that same child in seat 2 again, work out what's the next seat along where you could put the second child. So we've mentioned before we can't put it in 3. We've already put it in 4 in the previous configuration. So we'll put it in 5 there. And again, if we fill out the rest of the row with adults, that satisfies both conditions. Again, both children have two adults next to them, so that's fine. If we put another child there at the bottom in seat 2, and we then looked at the second child and put them across to seat 6, this wouldn't work because having a child in seat 6 again goes against that second condition, because that child in seat 6 would be sitting next to one adult. So at this point, there are no more configurations we can do with the child in seat 2, because the only two other seats that the second child could be in are seats 4 and 5. But what if we put this first child here in seat 3 instead? So I'm going to put the child there. We then can't have the second child in seat 4 for the same reasons mentioned before, but it could be in seat 5. So I'll put another one there in 5, and put the remaining seats full of adults. So at this point, again, both children have two adults next to them, and there are only two children in the whole row. So that works. You can see at this point that there's nowhere else we can go from here, because we've been kind of working across from left to right, row by row. So you can see we started here in the leftmost seat possible, and the second child is also in the leftmost seat that is possible. And then we kind of shifted across here with the second one, and then the first child also shifted across to the right. At this point, we can't push either of those two children any further to the right, because we can't have a child in seat 6, and therefore we can't bring this first child across any further either, because then they'd be right next to the other child, which again would go against the second condition. So at this point, we can't really go anywhere from here. We've found all the different configurations that fit both the first and the second condition. And so we can be pretty confident at this point that this table represents all the different combinations, and therefore the answer would be 8. Next question now, again, take a look at it. The reason I put this one in is I think it's a good demonstration of how to just generally sketch up a visual representation of whatever the question is showing you. Because most people learn and process things visually very well. So it's good to be able to know how to sketch up different diagrams and different schematics of whatever the question is asking you. So in this one we've got 6 different locations, A through to F, and there are various paths between these 6 different locations. So I would just simply draw something like this, where we've got the 6 different locations. Doesn't really matter where they're positioned, because the only thing that the question's asking us is about the paths between them. So it doesn't matter what order you have them in, so long as the paths between them are as we've got here. So I'm going to sketch up each of these 4 paths like so. You can see D to E, A to D, so on. And the question is asking us, if a player is not able to return to a location after taking an item from that location, which of the following additional paths out of our 4 answers would allow them to collect all 6 items, which are located in each of the 6 locations? So basically, which of these 4 proposed paths would allow you to get between all 6 of these places? Now, with this particular question, there's a shortcut, which is that if you look carefully at the paths we've got here, there's actually 2 separate circuits developing. We've got F, B, and C, and we've also got A, D, and E. So those are 2 separate circuits. You can see you can't actually get from one to the other. So the short way of doing this is just to work out which of these 4 paths provides a connection between the ADE circuit and the FBC circuit. You can imagine, for example, if you were on any of F, B, and C, there's no way of getting to A, D, or E. So if we go through these, a path between A and E, well, that wouldn't make any difference because A and E are on the same circuit. That wouldn't make any connections between the two. A and B might. You can see that they are two different circuits. So let's draw that in. Again, on the side of the page, you could just sketch this up quickly and see. So let's imagine we've got a path from A to B as option B proposes. Let's see how you could potentially get between all 6 of these without retracing your steps. I'm going to start down here with E, and you can see we can go from E to D to A to B. But at this point, you can either go from B to F or to C, but whichever way you go, you can't get to the other one. So in other words, we've gone from E to D to A to B, so those 4 are fine. But to finish off with both F and C is not possible, because if you go one way, you have to retrace your steps, regardless if you go to F or to C first. And retracing your steps is not allowed as per the question. So A to B also doesn't work, I'm afraid. Let's have a look at option C, which is B and D. Again, it's promising in that B and D belong to two of the different circuits. So if we connected those two, we'll just do the same again. B and D. So if we did this, well, we can see that if we went from E to D, we'd be stuck at this point because you could go from D to A up here, but then you'd be stuck. You'd have nowhere to go. And if you went to B, then you could either go to C or to F, but then you'd be stuck there. Either way, you can't quite get back to the A, so you can't get all 6. So again, C doesn't work. That leaves us with D, E, and F. Again, promising insofar as they're part of 2 different systems, so we'll sketch that in. And we'll just see if it's possible to get from all of them around here. If we start at C, go to B, through to F, down to E, to D, and then up to A. So pretty straightforward. It's just a case of knowing and being comfortable and readily being able to sketch up whatever the question shows you, particularly if it's describing some kind of system which you can quite easily visualize if you sketch it down on the page. You can see that this would be a pretty tough question if you didn't write anything down on the page or if you didn't sketch this up. But once you do so, it's really pretty simple. So yeah, as we found out, the correct answer is D. We'll go to the final part of the video now, which is Venn diagram questions. Now, to be honest, I think this is a style of question which is probably going out of style a bit, so you might not get one in the real paper, but I think it's still a good thing to go over. And it does fit under the topic of structures and tables and other diagrams you can use to solve problem-solving questions. So what do I mean by Venn diagram questions? Well, you may have seen classically these questions involve a number of different groups, often called silly names like blips and mips and dips. And the classic kind of question is saying something like blips can always be, or blips can be mips, mips are always dips, and so on. So you get information about how the different groups interrelate. Now the way I solve these is by sketching down on the side of the page a series of circles representing each of the different groups and how they interact or interrelate with each other. So in the end it turns out looking like a bit of a Venn diagram. That's just the basics of how to construct this. So I've got 4 different common instructions here that you might get. So in other words, MIPS are always blips would be up here on the top left, and you draw something like this. If you got MIPS may be blips, and then therefore may not be, then you'd sketch up something like this, and so forward. So take a minute to look through these and make sure they make sense to you. I think the first one here, A is always B, or, to give a practical example, MIPS are always blips, would look something like this. You've got the A group entirely enclosed within the larger B group, because it's saying that group A is always group B. So that whole group A has to be within group B. There's no part of it outside of that group. So this is how you would often start these questions, with something nice and simple like that. If you get an instruction saying A may be B, and therefore it might not be, I would sketch up something similar to this, where you've got the A and the B group just touching. The reason being it may be a situation where there is an overlap between A and B, so similar to this, or it may be a situation where the A and the B group are totally separate, like that. So because you don't know, because the instruction is A may be B, but might not be, I would just leave it as that, as them just touching, which in my mind means that they may be overlap, but there also might not be. That's why it's right on the border. If you have A is either B or C, so in other words, for example, MIPS are either blips or dips, what I would sketch up is what we have down here. So you've got the A group here, and the entire A group is on the background of either the B group or the C group. You can see the entire A group has either C or B in the background. Now, with the B and the C group, we don't know if they overlap or if they're separate. So it's similar to before up here. We don't know if these are overlapping or separate. All we know is that A is either B or C. So I leave the B and the C group, again, just touching to say that they could overlap, but they might be separate. That's all we know. Just finally, A is sometimes B. That's kind of the classic Venn diagram here, where you've got a section of overlap, but also a section which is separate. So these are the four common ones, I think. And when you go through these questions, it's just a case of starting with just a couple of circles and building up a picture from there based on the instructions you have. So we'll go to the first question now. So as you can see, we've got lots of silly names, and there's about 3 or 4 instructions here, 3 instructions in fact, based on how they interrelate. So begin with something nice and definite. I think rips are always blips is a good start point. So I would sketch up something like this. So you've got your blips group, but remember the rips are always blips, so the rips group is the one that goes inside. Now looking at the other 2 instructions, we want to build off this picture. So look for any other clues here which include either blips or rips, because that's our start point and our reference point now. So you can see the second one here, lips are sometimes clips, wouldn't be very good at this point, because for all we know, the lips and the clips could be totally separate off here, or they might be intersecting, or they might be inside. We don't really know where they are at this point. So at this stage, just leave that and go to the third one. Clips are either blips or dips. So this, have a read of this one. Clips are either blips or dips. This is the same as, if we go back to the previous slide, A is either B or C. And remember, we had our A group here kind of over the top of the 2 background groups because it's either in B or C. It's made up by both of them. So in this case, if clips are either blips or dips, we've already got our blips group here with the big circle. I'm going to put another circle next to it, which is the dip circle. And we don't know at this point if they're overlapping or not, so they're just touching. And it's our clips group that is made up of either blips or dips. So as before, we'll just write a little circle here. And you can see that that clips group is entirely composed of both the blips and the dips on either side. Now the final thing is just that second point that we skipped over before. Lips are sometimes clips. So we have to draw a lips group which is partially within the clips group, but also partially outside. So I'm going to sketch up something like that. Now again, we don't know if the lips group goes into the dips or the blips or even the ribs group. We know it's partially in the clips, but we don't know about the other ones. So I just kind of leave it there. It's not perfect, but just leave it sort of touching the other groups, just to say that it could be within, but it also might not be. So this technique is not perfect, but it's a good way of getting a rough representation of how everything interacts. And once you've got that, which we have at this stage, just go through the answers. So which of the following is true? And you can see our answers here are a combination of the above 4 possibilities. So 1, a blip cannot be a lip. Well, I would say it can be because you can see here a lip can be a clip and a clip can be a blip. So you can see this little area here where the lips and the blips could overlap means that's incorrect because a blip can be a lip. Now 2, a dip is always a clip. I would say that's incorrect because as you can see there's a lot of area here where there's dips but no clips. So that's not necessarily true. Obviously the clips group could be quite big, it could make up quite a lot of this circle, or indeed all of it, but we don't know that for sure. It's quite possible that it's that most of the dips are not clips. So again, 2 is out. At this point you could actually go straight for, well at this point you'd be down to B or D, so we're already doing pretty well. Option 3, a lip can be a rip. So remember, a lip can be a clip, and And as we can see here, the clip and the rip group are touching, which means that the clip group can overlap the rip group. So given a lip can be a clip and a clip can be a rip, I would say that a lip can be a rip. So 3 looks pretty good to me. And 4, a rip can be a dip. Well, again, remember that the blip group and the dip group are touching because we don't know if they overlap, but they very possibly could overlap. And if they do, then the dip group here could intersect the rip group as well, in which case 4 would be correct too. So 3 and 4 look like the best options out of the 4, and for that reason I would say that the answer would be D, 3 and 4. As I said before, it's not a perfect technique and not a perfect diagram. You can see that with examples 3 and 4, which we both said were correct, a lip can be a rip. Well, that's true, but if you look at the diagram, they're not actually touching. Likewise, a rip can be a dip, and yet they're not touching. So it does require that extension of thinking where you have to say, well, for example, with number 3, a lip can be a clip and a clip can be a rip because they're all touching. And therefore they could all be intersecting, and because of that, that's why a lip can be a rip. Likewise with 4, even though the rip and the dip group aren't touching in this diagram, because the dip and the blip group are touching, that means that they could intersect like a classic Venn diagram, and if that was the case, the dips group would likely intersect with the rip group. The other thing with this is the wording is important, because with 3 and 4 it's nice general wording of a rip can be a dip and a lip can be a rip. All we have to do is find one situation where that is true for that answer to be true. So in other words, if we have one situation where a lip can be a rip, or if it's just possible at all, then it is a correct answer. Whereas with 1, for example, a blip cannot be a lip, if we can find one example where actually a blip can be a lip, then all of a sudden that answer is wrong. So the wording is also very important. That's just a good general lesson for all of UMAT. So yeah, as I said, not perfect, but it's a much better way of doing it than just sort of trying to sift through all the words up here again and again and work out how things relate. So this one is very similar to before. If you want to pause the video and have a go sketching up a diagram, then please go ahead. This time we've got 4 different instructions, and I think the best one to begin with is probably here. All debs are clubs. You can do it any way you want, but I just like to start with a nice definite one. So if all debs are clubs, that means we need to have our clubs group like so, and enclosed within that is the debs group, because all of the debs are clubs. Now we want to look for something which you can build from. So we need to find another instruction which has either clubs or debs in it. I'm going to go for this one here. Some clubs are zips. So have a think about where we need to draw the zips group. Basically, the only condition we really need to satisfy is that it has to overlap the clubs group at some point, because some clubs are zips. Now, we don't know if that zips group also extends into the debs group, and we don't know if it extends out of the circle or out of the club circle altogether. So I'm going to sketch it up a bit like this. You can see it's just touching the border of the debs and also touching the outside border of the club circle, just to say it could extend out this way and or inwards this way. But all we know for sure is that some of the clubs group is also part of the zips group. Now we've got 2 more instructions. Some bops are zips and most debs are bops. So basically we've got one more group to draw, which is the bops group, and there's 2 instructions relating to it. So here it says some bops are zips. That just means that our bops group, when we draw it, has to overlap the zips group at least partially. And the other instruction is that most debs are bops. That means that our bops group, when we draw it, has to cover most of the debs group here. So between those 2, I'm going to draw it up like so. You can see that our bops group here covers most of the deb group and also overlaps part of the zip group. So this is roughly what I would have as the final diagram. If you sketch yours up before, hopefully it looks fairly similar to that. If we go to the question now, which of the following is true? Option A, most clubs are bops. So this is one where, I mean, it could be true. We know that certainly the bops group here covers most of the deb group. That was given to us here in the final statement. And so if the debs group covers most or all of the club group, then I guess it could be true that most clubs are bops. The issue really is that we just can't be sure because we don't know anything about the size of the debs group. It could be very big or it could be very small. So that's one way you just can't be sure, and therefore it's probably not the best answer for a very definite question like which of the following must be true or is true. With B, zips can be debs. That looks pretty good to me because you can see we've got the zips group here and the deb group there touching, which recall means that they can overlap like a classic Venn diagram. So given the nice general wording here of zips can be debs, I would say that they certainly can be. They might not be, but they certainly can be. So that's a pretty good answer. I'd be going for that at this stage. With C, all clubs are bops. As we can see again, probably not true. The bops group only covers part of the club group, so it's very unlikely. And given only most debs are bops, that means that the bops group is going to be a bit smaller than the deb group, and the deb group is no bigger than the club group, so it probably can't be true. Just finally, D, most clubs are zips. Again, you can't really say for certain. The zips group can be quite small, as in our diagram here. And given option B, we know can definitely be true. I'd say that's the best option out of the four, so B. We'll go to our final question now. Same as before, we've got 4 different instructions detailing 4 different groups and how they interrelate. Well, actually, it might even be 5 different groups in this question, but same process. So begin with something you know for sure. I'm going to go with this instruction here. Wraps are always mops. So as we know, just draw up the mop circle, and within that, sketch up the wrap circle. So now we're looking for something which we can build from either the mops and or the wraps. I'm going to go for this one here. Leps are either bips or mops. So remember, when you have an instruction like this where it's A is either B or C, the way to do it is as follows. We've already got our mops group on the page, but we have to draw up our bips group just touching it, because at this stage we know that the leps, which I'll put here, overlap both the bips and the mops, but we don't know if the bips and the mops themselves overlap or whether they're separate. So the bips and the mop circles just touch, and we have the lep circle overlapping. Now there's only one more component to put in this one, which is the hoops, and there are 2 instructions. One is that hoops are sometimes mops, so that means we have to have our hoops circle partially intersecting the mops group, like a classic Venn diagram. And the other instruction is that bips are never hoops. So we have to have our bip circle here totally separate from the hoop circle. So I'm going to sketch up the hoop circle like so. You can see I've got a definite gap here between the 2, saying that they never interact. And we've got that intersection between the hoops and the mops as per the first instruction. So and also the other thing to notice here is that the hoop circle just touches the leps and the wrap circle, because we don't know if it extends into those 2 or if it falls short, and if they're therefore separate. So which of the following isn't true? Notice that negative. So hoops can't be bips. Well, it's true that hoops can't be bips. We've got them separate here, as per the instruction here that bips are never hoops. So I would say that that's not a good answer, because we're looking for which of the following isn't true. Keep going through. Wraps can be bips, sorry. Well, I would say they can be, because you can see the bips and the mop circle are just touching, which means that they could intersect like a classic Venn diagram. And given the wraps group is inside the mops group, it is possible that the bips group here could extend such that it intersects the wraps group like so. So this option B, that is possible, and therefore it isn't the best answer. With C, bips can be mops. Again, same thing, the bips and the mop circles are touching, so they could intersect, in which case that would be a fair answer, that would be correct. And for that reason, again, it's not true. Finally, leps can't be hoops. Well, we can see that the leps and the hoops group are touching again. As we mentioned before, we know that the hoops and the mops group are intersecting as we've drawn, and the leps group is part of the mops group. So it's possible that the leps and the hoops could intersect. And for that reason, leps can be hoops, which means which of the following isn't true? I'd say D would be the best option out of the 4. So D is the correct answer. That's all for this video. I know it's been a pretty long one, but this is really the main part, the crux of problem solving in section 1, is being able to sketch up diagrams and tables and just know how to set things out. So I hope it's been helpful.